Hello, good evening friends, good evening students. Today we discuss the biomolecules. Okay, what are these biomolecules? Types of biomolecules, and also especially mainly we focus on carbohydrates, proteins, amino acids and vitamins. Understand? Some of their properties, preparation, etc. the structures we'll study in this class. Now we'll see one by one. What are these biomolecules? So biomolecules are produced by living organisms. Examples: carbohydrates, proteins, nucleic acids, lipids, etc. So these are carbohydrates and proteins are the essential constituents of our food. So these biomolecules interact with each other and constitute the molecular logic of life processes. So some simple molecules like vitamins and minerals play an important role in the functions of our organisms. Now, one of the important biomolecules is carbohydrates. Now we'll see what are carbohydrates. You see, the name carbohydrate indicates these are nothing but the hydrates of carbon. You see, they form a very large group of naturally occurring organic compounds. Example: cane sugar, glucose, starch, etc. So the name carbohydrate means hydrates of carbon, and most of them will have a general formula CHH2O taken Y types. Understood? So the molecular formula of glucose, the general molecular formula is C6H12O6, which can be written as C6H2O taken 6 times. So that means, but all other compounds which fits into this formula may not be carbohydrates, and there are some compounds which may fit into this formula are not carbohydrate. We will see some of the examples. For example, CH3COOH. So the glucose is fitting in this formula C6H2O taken 6 times. It is a carbohydrate. But whereas acetic acid also fits in this formula. Its formula is C2H2O taken twice, but it is not a carbohydrate. So that's why we cannot generalize. Whereas rhamnose, another example, C6H12O5, though it is not fitting in this general formula, but it is a carbohydrate. Okay. Now, so these carbohydrates may be defined as optically active polyhydroxy aldehydes or polyhydroxy ketones, which on hydrolysis give simpler units. For example, which are sweet in taste. So carbohydrates which are sweet in taste are called sugars, which are not in sweet in taste are called non-sugars. So for sugars, example sucrose and lactose, which is present in a milk. So now it is carbohydrates are also called saccharides. So what is the meaning of saccharide? That means saccharide means sugar. Now we will go to the classification of carbohydrates based on their behavior towards hydrolysis. So that means first one is a monosaccharide. So what is a monosaccharide? A saccharide or a carbohydrate that cannot be hydrolyzed further to give simpler units of a polyhydroxyaldehyde or ketone is called a monosaccharide. For example, glucose and fructose. So on hydrolysis we cannot get back, or we cannot get a still simpler units. So that is a monosaccharide. For example, glucose, fructose and ribose. That is a monosaccharide. What is a oligosaccharide? So that means, oligo means the carbohydrates which on hydrolysis give 2 to 10 monosaccharide units. So that is which give 2 to 10 monosaccharides on hydrolysis are called oligosaccharide. So these oligosaccharides again are classified as a disaccharide, which give 2 simpler units on hydrolysis, trisaccharides which give 3 units, or tetrasaccharide, etc. So like this, the disaccharides, trisaccharides, tetrasaccharides, etc. depending upon the number of monosaccharide units they produce on hydrolysis. Clear? So for example, disaccharide. One of the important examples of disaccharide is sucrose, which on hydrolysis gives 1 unit of glucose and 1 unit of fructose. So it is a disaccharide. If you add water to sucrose, we will get 1 molecule of glucose and 1 molecule of sucrose. So this is given. Sucrose and hydrolysis give one molecule each of glucose and fructose. So whereas another disaccharide called maltose gives two molecules of glucose only. Now next comes the polysaccharides. So the meaning, the word poly means many or large. So that means those carbohydrates which on hydrolysis give a very large number of simpler units. They are called polysaccharides. We can take starch, cellulose, etc. as the examples for polysaccharides. So starch, cellulose, glycogen, gums, etc. So these polysaccharides are not sweet in taste. So earlier we have seen some oligosaccharides. So which are sweet in taste, they are called sugars. Which are not sweet in taste, they are called non-sugars. Okay. So that means these polysaccharides are generally they are not sweet in taste. So therefore they are non-sugars. Now these carbohydrates may be either classified as a non-reducing sugars or reducing sugars. Again, depending on the group present. That means whether free aldehyde group is there, free ketonic group is there, whether they reduce the tolerance reagent and failing solution. So they are again classified as a reducing sugars and the non-reducing sugars. So that is given here. All those carbohydrates which reduce failing solution and tolerance reagent are referred to as reducing sugars. Otherwise they are non-reducing sugars. For example, aldoketones or aldohexose, they are reducing sugars. That is glucose and fructose come under reducing sugars. Next slide. So that is so in disaccharides, if the reducing groups of monosaccharide, that is aldehydic or ketonic group, are not free or not bonded, so they are called non-reducing sugar. Example, sucrose. So if the reducing groups of monosaccharide, that is aldehydic ketone groups, are bonded, so if these are bonded, if they are not free, this aldehydic ketone group, they are called non-reducing sugars. So example is sucrose. Sucrose is a non-reducing sugar. Sugars in which these functional groups are free. So that means if free aldehyde group is there, they can reduce tolerance agent and failing solution. Such sugars we call it as a reducing sugars. Example is maltose and lactose. Understand? So therefore, we have to see the difference between the reducing sugars and non-reducing sugars, and which come under reducing sugars and which come under non-reducing sugars. Maltose and lactose are reducing sugars, whereas sucrose is a non-reducing sugar. Next slide, monosaccharides. Now we will come to the monosaccharides. One of the important monosaccharide is glucose, because which will not give any simpler unit on hydrolysis, and we will see some of the preparation methods of preparation of glucose and the structure of glucose in this chapter or in this class. So that means these monosaccharides are further classified on the basis of number of carbon atoms and functional groups present in them. So what is the number of carbon atoms present and also the functional group? If a monosaccharide contains aldehyde group, it is known as aldose. Okay. So if a monosaccharide contains an aldehyde group, it is called aldose, and if it contains a keto group, it is called ketose. Now we see if it contains 3 carbons, triose, 4 carbons, tetrose, pentose, like that. So depending on the number of carbons. Now you see the table, different types of monosaccharides containing the number of carbons and whether the general term is 3 means triose, 4 means tetrose, 5 carbons means pentose, 6 carbons hexose, 7 carbons heptose. Again, based on the functional group, if the 3 carbon monosaccharide contains aldehyde group, it is called aldotriose. If it contains keto group, it is called ketotriose. Similarly, aldotetrose having 4 carbons, ketotetrose. Aldopentose having 5 carbons with aldehyde group, ketopentose having 5 carbons with the keto group. Understood? So hexose, aldohexose and ketohexose. So therefore, this aldohexose and ketohexose, that is glucose is aldohexose. We will see when you see the structure, it is having glucose, the aldehyde group and with 6 carbons. So fructose is called the ketohexose. That means it contains a keto group with 6 carbons. That we will see in the next slide. Go to this preparation of glucose. So how is glucose prepared? So that means one of the methods of preparation is cane sugar. So that means Glucose occurs freely in nature as well as in the combined form. So mainly it is present in sweet fruits and honey. Ripened grapes also containing glucose in large amounts. Ripe grapes. Okay, that is the main source. Honey and sweet fruits and ripe grapes. Understood? So also it is prepared from sucrose. That means already we have discussed, because sucrose is a disaccharide which on hydrolysis in presence of HCl or H2SO4 gives one molecule of glucose and one molecule of fructose. So therefore, the sucrose solution, it gives in alcoholic solution on boiled with HCl or H2SO4 gives one molecule of glucose and fructose in equal amounts. This is the formula, chemical formula. This is sucrose. With water, you are getting glucose plus fructose. C12H22O11 plus water gives one molecule of glucose, one molecule of fructose. Another method is from starch. So it is a polysaccharide. So that means starch, glucose is also obtained by hydrolysis of starch by boiling with either dilute H2SO4 under this temperature and pressure. So that means it is a polysaccharide. The general formula is C6H10O5 plus NH2O gives rise to, on hydrolysis you will get N molecules of glucose. So therefore starch is a polysaccharide of glucose. So it gives N molecules of glucose. N may be a very large number, maybe 100, 1000, etc. So therefore there are two methods. One is from cane sugar, another one is from starch. So these are the two methods of preparation of glucose. Now, when you come to the structure of glucose, after seeing the molecular formula, so molecular formula just represents C6H12O6 containing 6 carbons, 12 hydrogens and 6 oxygen. So how are they? So now we'll see what are the various functional groups present in it. So that is all coming under structure. So glucose is already known as aldohexose. The name itself indicates, that means glucose contains an aldehyde group. Hexa stands for 6 carbon. So it is a 6 carbon aldehyde. That much we can say from the name. And is also known as dextrose. Okay. It is a monomer of many of the larger carbohydrates. That means we can see starch also we can get, because it is the monomer of starch. It is also the monomer of glucose, etc. So it is the most abundant organic compound on earth. What is the structure of glucose? You see, it is written like this: CHOH taken 4 times, CH2OH. So that means there is an aldehyde group at the top. There are 4 OH groups, that is a primary, secondary OH groups, functional groups, secondary alcoholic groups 4 and CH2OH, one primary function. This is the proposed structure for glucose. Okay, CHO, this is called, totally there are 6 carbons and one aldehyde group. So that is why it is known as aldohexose. Next, evidences for the structure. So, what are the evidences for the structure of glucose? That means, how can you know that there are 6 carbons? How can you know that there are 5 functional groups, that 5 hydroxy functional groups or one aldehyde group, like that? So, there are some evidences. We can go through some reactions, chemical properties. So, its molecular formula is C6H12O6. So, that means first reaction is on prolonged heating with HI. So, that means that glucose is heated with the hydrogen iodide. So, you will get N-hexane, indicating that there are 6 carbons in a glucose. So, this reaction indicates when it is heated on with HI. So, we are getting N-hexane, indicating there are 6 carbons in a linked in a straight chain. So, that means the glucose HI heat, you are getting N-hexane, a straight chain compound. So, all the 6 carbons are in straight chain. This is one of the evidences for the straight chain structure. Next, it is reacting with NH2OH. When it is treated with NH2OH, that is hydroxylamine, you are getting an oxime derivative. So, that means there is CHO means one second. So that means glucose in reaction with NH2OH, a hydroxylamine. So all these structures you have studied under the organic chapter, that is properties of aldehydes. So hydroxylamine, you will get this CH double bond in OH. So formation of this compound indicates, that means there is an aldehyde group. So that means glucose reacts with hydroxylamine to form an oxide. Same glucose, when it reacts with the hydrogen cyanide, so we are getting cyanohydrin, CHOHCl. So this structure you are getting, that is called a cyanohydrin. So it indicates that there is an aldehyde group. So it is possible only when there is a aldehyde group. Aldehydes with hydroxylamine give oxide. This structure we call it as the functional group CH double bond NOH. We call it as the oxide derivative. This structure we call it as a cyanohydrins. That means aldehydes with one molecule of HCN, you will get a cyanohydrin. This is a type of structure CNOH. Next, what is the next evidence? That means glucose is oxidized with a mild oxidizing agent like a bromine water to give gluconic acid. That means how it converts, that means aldehydes are oxidized to further carboxylic acids. The CHO group is oxidized to COH group. So this is another evidence. That means there is a aldehyde group. When you get a gluconic acid, that means COH, it is possible only when there is a CHO, because Br2O water is the mild oxidizing agent. So aldehydes on oxidation give carboxylic acids. That is another evidence. Next, acetylation of glucose with acetic anhydride. So what will happen to the glucose when it is treated with the acetic anhydride? That means you are getting a pentaacetate. It gives, this glucose gives a pentaacetate. It means 5 molecules of acetate, indicating that there are 5 OH groups. That means there are 5 hydroxy groups in a glucose. So on treatment with acetylation or acetic anhydride, so glucose on acetic anhydride, you will get CHO, CH3 taken twice. That is called a pentaacetate. So that means all the 5 OH groups are converted into OCOCH3. That means acetyl group is introduced in the place of hydrogen. H is replaced by OCOCH3. That is called CH3COO group. This COCH3 group, that is called acetyl group. It is called a pentaacetate. So treatment of glucose with the acetic anhydride formation of pentaacetate gives there are 5 hydroxyl groups in a glucose. Next. So next oxidation reaction with the nitric acid. When glucose is treated with a strong oxidizing agent like nitric acid, now you see glucose already on oxidation, you have got a gluconic acid. That means with the bromine water. So glucose directly on oxidation with the HNO3, you will get both gluconic acid as well as the glucose. They give saccharic acid. That means nitric acid is a strong oxidizing agent. Either gluconic acid or glucose on oxidation, both directly on oxidation with the nitric acid. You must write here HNO3. You are getting first and last carbon converted into the COH, that is called saccharic acid. It is a dicarboxylic acid. It is a dicarboxylic. It is another evidence for the glucose. Now, when you come to the structure, that is a Fischer formula. First, straight chain structure is proposed by Fischer. So that means, what is this? Structure means what are the arrangement, what are the spatial arrangement of various, how the various OH groups are there, how the carbons are there, how is the CHO group. These are all coming under structure. That is the spatial arrangement of various functional groups present. The exact spatial arrangement of different OH groups given by Fischer represented as structure. So it is a person who first introduced the structure of glucose. That is called this structure, structure 1. That means all CHO on the last carbon. First carbon is a primary alcohol. Like this, it is given in the straight chain. So out of 5 OH groups, 4 OH groups are a secondary functional groups, and last one is a primary functional group. Now you see these cross lines are horizontal. Out of 4 OH groups, how are they? HOH, they are towards right side. Another one is the left, right. Wait. Now you observe. So you see the structure. Structure 1, you observe structure 1. That means glucose HCHO. From the bottom, if you come HOH, H is towards left side, OH is towards right side. Next, alternate OH. So this is the Fischer projection. In the second structure, gluconic acid and stearic acid. In the gluconic acid, this is the gluconic acid. Only the difference is between gluconic acid first structure and this one. The CHO is oxidized to COH. In the last structure, that is a structure 3, third structure, that is both the end carbons are oxidized to COH. That is called stearic acid. That is called the stearic acid. This is the structure proposed by Fischer. So that is Fischer formula. Next we will see the glucose is generally named as capital D plus glucose. So what is this capital D? What is this plus? So that means where D represents only the configuration. That we will discuss shortly within next slide. We will see capital D is the just configuration and plus represent the dextrorotatory nature. That means it rotates the plane polarized light towards right side. That is positive symbol. Plus symbol represents the dextrorotatory nature of the molecule. Capital D is only representing the configuration. That will come to know by taking one example. That is a glyceraldehyde. So this capital D and small d are quite different. So capital D is nothing to do with the dextrorotatory nature. Capital D is different. Dextrorotatory will denote the symbol small d. That is which rotates the plane polar light. In the first chapter we have to discuss towards right side. Such compounds we call it as a dextrorotatory, denoted by small d before the name of the compound. So that means capital D represents the configuration and plus represents the dextrorotatory nature of the molecule. So D and L, capital D and L. Once again I am stressing capital D and L have no relation with the optical activity. That is different. Small d, small l only are denoted to know the that is the optical rotation. That means optical rotation or optical activity. Of course, they indicate the relative configuration of particular isomer of glyceraldehyde. So we will come to know what is capital D, what is capital L by taking the arrangement of aldehyde and hydroxy group with reference to the glyceraldehyde, which is a D-glyceraldehyde and which is a L-glyceraldehyde. We will come to know, which contains a symmetric carbon and this group. Now we will come to the glyceraldehyde. Yes, you see, this is plus glyceraldehyde, this is minus glyceraldehyde. That means glyceraldehyde having 3 carbons. Out of that, one aldehyde group, 2 OH groups. Out of one 2 OH groups, the middle carbon is an asymmetric carbon. Here we have to discuss the middle carbon is asymmetric carbon. What is an asymmetric carbon? The carbon which is surrounded by 4 different groups. You know, the valency of carbon is 4. So if you see the point where the 2 lines intersect, that is a carbon. Okay. So what are the various different groups present around this carbon? One side H, another side CHO, another side OH, another side CH2OH. So the carbon to which all the 4 groups are defined, you say it is an asymmetric carbon. So therefore, this glyceraldehyde is a plus glyceraldehyde. That means this plus sign indicates it is a dextrorotatory. It is a dextrorotatory. You observe the next structure. So it is denoted as minus glyceraldehyde. What is the difference between first and second structure? Only in the arrangement of HOH on the middle carbon. Here in the first carbon, in the middle carbon, H is left side, OH is right side. So here OH is left side, H is right side. That orientation, or we can say the spatial arrangement of H and OH groups on a symmetric carbon makes them 2 different isomers. One is a plus isomer, this is called minus isomer. That means it rotates the plane polar light towards left side, whereas this rotates towards the right side. Understood? Now, next, with respect to this, we take the glucose as a D or L. Yes. So, all those compounds which are chemically correlated to plus isomer of glyceraldehyde, which are chemically correlated to plus isomer of glyceraldehyde are said to have D configuration, capital D. So once again you go through the plus, that means yes, here we see plus D plus glyceraldehyde. So we are discussing this. All those compounds which are chemically correlated to plus isomer of glyceraldehyde are said to have D configuration, whereas those are related to minus isomer are said to have capital L configuration. Understood? So the structure of glucose compared to glyceraldehyde with respect to the position of OH group present on the lowest asymmetric carbon as given below. So now we will compare the glyceraldehyde with that of our glucose. Yes. Now we will say glucose one side, this is the glyceraldehyde on the other side. So last but one. So here from the bottom the second carbon. So how are the arrangement of H and OH? That means you compare this up. This is also having CH2OH, HOH. This is also having CH2OH, HOH. So now the orientation or spatial arrangement of the lowest asymmetric carbon. The spatial arrangement of lowest asymmetric carbon on both the carbons are same. So therefore this is H left side, OH right side. So therefore this is called capital D plus glyceraldehyde. This is here also the lowest asymmetric carbon is this one. So these are also asymmetric carbons only. So that means if the arrangement of H and OH is similar to that of this glyceraldehyde, that is considered as D, capital D. So therefore this is called D plus glucose, this is called D plus glyceraldehyde. So remember that by comparing the spatial arrangement of H and OH with respect to glyceraldehyde, the name capital D is given before the name of the glucose, that is called capital D. Next. So now you see the cyclic structure of glucose. So though Fischer has introduced the straight chain structure, but it will not respond to some of the properties of the glucose. That means the structure 1 of glucose, that is which is proposed by Fischer, explained most of its properties, but the following reactions could not be explained by this straight chain structure. Okay. Now, what are the structure tests which could not be responded? Glucose does not give Gibbs test, and hydrogen sulfide addition product with NaHSO3 despite having the aldehyde group. So, actually, if the aldehyde group is there, it must respond to the Gibbs test and with hydrogen sulfide, sodium hydrogen NaHSO3, but it is not responding. We'll see what will be the reason. The pentastate of glucose does not react with hydroxylamine, indicating the absence of free OH. So this glucose proposed by the Fischer, it is not responding. This pentacetate is not responding with hydroxylamine. So what is the answer? Why it is not responding? The hydroxylamine with the hydroxylamine, because indicating the absence of free aldehyde group. That indicates that aldehyde group is not free. If it is not free, how is it? Next question. So therefore, the straight chain structure is not satisfied. They go for the cyclic structure. So the cyclic structure of glucose. What led the cyclic structure of glucose? Because the glucose is not responding to some of the reactions. The interconversion of alpha and beta could not be explained by open chain structure. So that means how alpha and beta glucose are interconverted. Okay, that is not explained by the open chain structure 1 for glucose. Since one of the OH groups may add to the CH2 group and form a cyclic hemiacetal structure, and glucose forms a 6-membered ring. So that means why the interconversion of a glucose, alpha glucose and beta glucose, it is not explained by the primary, that is glucose structure 1, which is given by the Fischer, because it is involved in a cyclic formation, that is C5, OH of C5 and a CHO group. That we'll see in the next slide. So that means, and forming the OH group may add to the CHO group. So this way we have studied how aldehyde combines with the OH group, that is alkyl group, forming hemiacetal. Hemiacetal. It forms a cyclic hemiacetal structure, and glucose forms a 6-membered ring, in which we see OH carbon 5 is involved in ring formation, which explains the absence of a CHO group. So, as the CHO group on first carbon, on the 6th carbon is involved in the ring formation with the OH of the 5th carbon. So, that is why it is not the free aldehyde group is not present and cannot respond to some of the properties. So, and also existence of glucose in two forms. That is why open chain structure could not explain the interconversion of alpha and beta. It is possible only when it exists in a cyclic form. Now, come to this. Yes, here it is neatly explained the formation of a cyclic structure, that is called hemiacetal form. So, this is first structure proposed by the Fischer. So, here what is showing through arrow marks? This is, you count the carbons from the top. Carbon 1, aldehyde 2, 3, 4, 5, 6. 2, 3, 4, 5. So don't confuse, always count the number of carbons from the top. 1, 2, 3, 4, 5, 6. Understand? So, if there are two different according to UPSC, so to give preference to the aldehyde group. That is number 1. Okay. Now, this arrow mark shows, that means the OH, that is O of 5th carbon, C5, it is called a hydroxyl group of carbon 5 interacts, forms a ring with the aldehyde group. Yes, with the aldehyde group. When it combines with the OH group, C double bond OH combines with this, there are two structures result. It results in two different structures. So, you see this one. What will happen here? You see, where the H will go? H will go to the C, CO. So, this hydrogen will combine with O. So, that is resulting as COH, and this O is in between connected to C1, C5. So, that means between C1, C5 there is one oxygen. So, and the hydrogen of OH will go to this oxygen, C double bond. So, forming COH and COH. Now, you see the structure, this is middle structure, this structure and this structure. What is the difference between? So, that means C5, OH of C5 and the aldehyde will form two different structures. Now, difference you observe here, first carbon H is left, OH is right. Second carbon OH is left, OH is left, H is right. So, except the arrangement of HOH on carbon 1, the other things are same between this and this. So, these two isomers, these are cyclic structures of glucose, now which differ in the arrangement of H and OH only on the first carbon. So, such isomers we call as anomers. Anomers. And moreover, this glucose is called alpha, this glucose is called beta. Why the alpha beta name came? Just because of the arrangement, spatial arrangement of H and OH on carbon 1. That's the only difference. This first and the last structure. So here H is left, OH is right. Here OH is left, OH is right. So therefore it is called alpha D glucose. This is called beta D glucose. So with a small difference in the spatial arrangement of H and OH or orientation of H and OH. So this alpha glucose starch. This is cellulose. Understand? The polymer of beta glucose is cellulose, the polymer of alpha glucose is starch. So therefore, starch we can digest because it's a polymer of alpha glucose. Cellulose because plant matter, we cannot digest it. So just that is called structural difference between alpha glucose and the beta glucose, which is clearly shown in this structure. So only such isomers, we call it the anomers, which differ on the spatial arrangement of H and OH on carbon 1, are known as anomers. Okay, these two forms differ only in the configuration of OH group at C1, called anomeric carbon. That C1 is called the anomeric carbon, and they are called the anomers. Clear? The 6-membered cyclic structure of glucose. So, when the C5, OH of C5 forms a cyclic ring with the C1, so automatically it forms a ring structure. How to write the ring structure of the glucose? That means it results in two different 6-membered cyclic structure. One is alpha, this is called pyranose structure. This is called a 6-membered ring called pyranose, and it is called the pyranose structure. Pyran is a cyclic organic compound with 1 oxygen atom and 5 carbon atoms in the ring. So what is pyran or pyranose? We'll see. So this is pyran. This is the Haworth structure. So that means based on the cyclic formation, the C5, OH of C5 and aldehyde group. So we are getting alpha D glucose and beta D glucose. So which can be written in the form of a cycle by forming a ring structure for this. That is called Haworth structure. So that means we can show it on the board. That means again, what to do? We have to make a 6-membered hexagon. So like this, we will get HOH, HOH. Now you observe alpha D glucose and beta D glucose. So how is the arrangement, spatial arrangement of HOH on both? This is cyclic structure. First carbon, second carbon, draw vertical lines, third, fourth, fifth. Here also first, second, third, fourth, fifth. So of course always the 6th carbon is on the top on both. CH2OH, CH2OH. Now if you arrange, you just see the difference. First carbon, this is alpha D glucose, this is a beta D glucose. When it is shown in the form of cyclic structure as a pyranose structure, again you can see the orientation of H and OH and first carbon. Here H is on the top, OH is on the bottom. In the beta, OH is on the top, H is, except this arrangement, everything is same. HOH, HOH, OH, HOH. So this is the Haworth projection or Haworth structure for cyclic structure for glucose. That is the pyranose structure. Similarly, fructose. So another carbohydrate monosaccharide is known as fructose, known as ketohexose, having 6 carbon, 1 keto group on the 5th carbon. So that means from the top, second carbon is a ketohexose. So the ring structure is like this: alpha D minus. Here D minus is put before. So that means it is a levorotatory. Fructose is a levorotatory. Understood? Whereas for glucose we see plus. It is called dextrorotatory. Of course, alpha D, beta D. This is a cyclic structure. How the C5 will combine with the ketonic group, second carbon, where it resulting in OH, CH2OH, OH, CH2OH. These are the two ring structure for the fructose. Yes, you see the cyclic structure of same thing can be written in the form of 5-membered ring, furanose structure. It is called a furanose. Only 5-membered, one corner is occupied by the oxygen group. It is called fructofuranose. Alpha D minus is a beta D minus. Again, you can see the arrangement on first and second carbon. CH2OH top, OH down. OH top, CH2OH down. So this is again a Haworth structure for the fructose. Now, disaccharides. So, disaccharides already we have seen by definition. That means the carbohydrates which are hydrolysis give two simpler units. Best example is sucrose. Sucrose and hydrolysis give one molecule of glucose and one molecule of fructose. So, how these disaccharides? A linkage between two monosaccharide units through oxygen by losing a molecule of water. So here it is a combination of two glucose units. When the two glucose units are joined together, when two monosaccharides is joined together to form a disaccharide by losing a molecule of water, and during that they are connected by a oxide linkage, that is called glycosidic linkage. Lose a molecule of water is called a glycoside. That link is called through oxygen. We call it as a glycosidic linkage. So the best example is the sucrose, which on hydrolysis gives a equimolar mixture of glucose and fructose. Of course, D glucose and D minus fructose. Yes, here we can see the structure of sucrose and the glycosidic linkage. So how glucose and the fructose are linked through oxygen. This oxygen linkage between two units. This is called the glycosidic linkage. Understand? Okay. Here C1 of glucose and C2 of the fructose. They are having the glycosidic linkage. C1 of glucose and C2 of fructose. Next, lactose is another is a disaccharide milk sugar known as milk sugar. Of course, here one galactose and glucose, they have a glycosidic linkage. Yes, maltose. Yes, this is the sucrose. Of course, now it's the inversion of sucrose. So that means, yes. So by glycosidic linkage, so on which carbon C1 of alpha glucose and C2 of fructose. So that means, yes, reducing sugar, the reducing groups of glucose and fructose are involved in glycosidic bond formation. So that means here both the functional groups, aldehyde and keto groups, are involved in bond formation. They are called non-reducing sugar. So this means these functional groups are not free. So why is it called invert sugar? Sucrose is called inversion. That means invert sugar means on hydrolysis sucrose gives one molecule of D plus glucose and one molecule of D minus fructose. Yes, dextro, glucose is a dextro, whereas fructose is a levo. That is why hydrolysis of sucrose brings about a change in the sign of rotation from dextro to levo, and the product is named as invert sugar. And this process, that means actually sucrose is a positive dextrorotatory, which on hydrolysis gives one molecule of sucrose, one molecule of glucose, dextro, and one molecule of levo. That is making it overall compound as a minus. Hydrolysis of sucrose brings about a change in the sign of rotation from dextro to levo. So that is why it is named as a invert sugar, and this process is known as inversion of sugar. Next, another disaccharide is called maltose. So which is made of two glucose units with the glycosidic linkage between C1 of one unit and C4 of another unit. So there is this O linkage through oxygen is known as a glycosidic linkage. C1 of one unit and C4 of another unit. This is also a disaccharide. Now lactose is also a disaccharide. D-galactose, beta and D-glucose, beta-D-glucose. Again, a C1, C4 glycosidic linkage between C1 and C4. Of course. Next, another we will come to the polysaccharides. Under polysaccharide, starch. The best example is starch. It is a polysaccharide of alpha glucose. So that means there are two types. One is amylose and amylopectin. Starch is a polysaccharide of it's a polysaccharide. It's a polymer of alpha glucose. So that means generally is a homopolysaccharide made formed by only one unit of glucose. That is polymer of glucose only. It is a reserve food material in plants, potatoes, rice, wheat, etc. That means starch consists of two parts. So briefly we will see what is the starch contains amylose. Amylose, that means 15 to 30% of starch is obtained in the form of amylose, which is a water soluble and straight chain compound. Okay. Next one is amylopectin. That is it's a water soluble unbranched. That means a straight chain. So this is the structure of unbranched amylose. Okay, all the glucose molecules are linked by 1 to 4, alpha 1 to 4, glycosidic linkage between 1 and 4, 1 and 4, 1 and 4 like that. So only this much you know, that is starch contains two parts, amylose, 15 to 30% of starch exists in the form of amylose, which is water soluble and non-branching. Okay. Next is amylopectin. Of course, is insoluble in water. 85% of the starch occurs in the form of amylopectin. So it is a branched chain polymer and insoluble in water. So this is the structure of amylopectin. So there are nothing to do about the structure of only the basic ideas, the different structural difference between amylose and amylopectin. That much only you must know it. Next, this is cellulose. Cellulose is another polysaccharide. That means which is purely made of beta glucose. It's a polymer of beta glucose. Again, you must know the difference between alpha glucose and beta glucose. These are anomers. So, it's important one more question. What are anomers? Why alpha and beta glucose are called anomers? Because they differ in the orientation of H and OH on carbon 1, C1. So, they are called anomers. That carbon is called anomeric carbon. Starch is a polymer of alpha glucose and cellulose is a polymer of beta glucose. This is the cellulose structure. It will repeat. That means many glucose units linked together to form a cellulose. Generally, it occurs in plants and most abundant organic substance in plant. It constitutes the cell wall of plant cells. So most of the cell wall is a cellulose. Okay. This is regarding glucose unit. That is very important. Now, another polysaccharide, this is glucosen, glycogen. So, which is stored in animal body as glycogen, known as animal starch, because its structure is similar to amylopectin. Its glycogen structure is similar to the amylopectin, which is water insoluble and a branched chain structure. Of course, it is highly branched. It is present in liver, muscles, and brain. When the body needs glucose, enzymes break the glycogen down to glucose. Of course, glycogen is also found in yeast and fungi. Next, we see the importance of carbohydrates. After knowing the properties of the preparation and properties of glucose, the straight chain structure and the ring structure, how to write the ring structure from straight chain structure, what is anomeric glycosidic linkage, next cellulose, starch, their monomers. Now, importance of carbohydrates. Carbohydrates are essential for life of both plants and animals. They form a major portion of our body. So, these are called as storage molecules. As starch in plants and glycogen in animals. Cell wall of bacteria is made up of cellulose, furniture from cellulose in the form of wood. So, these are some of the importance of carbohydrates. Next important concept is amino acids. So, briefly we discuss what are amino acids. The name itself containing an organofunctional groups containing one amino group as well as the acid group COH. So these are the derivatives of methane. So how amino acid is obtained from the methane? Methane means CH4. So where out of 4 hydrogens on carbon, 3 carbons, 3 hydrogens are replaced by different group. One NH2 group, one COH group, another one R. This is alkyl group. So that is called an amino acid. These are organic molecules derivatives of methane. One hydrogen atom is replaced. Suppose this is a methane structure. One side one hydrogen is replaced by NH2 group, another side is replaced by a COH group, another one is a side chain capital. So that is a derivative of methane. So amino acid. Amino group is there, acid group is there. That is called amino acid. So the polyamino acids are nothing but proteins. Now we will discuss here what are different types of amino acids, what are essential amino acids, non-essential amino acids, and what is the peptide bond, dipeptide, tripeptide, etc. Yes, so this is one important, the simplest amino acid is here. If that R is also a H, this is called a simplest amino acid glycine. This means if this H is replaced by one CH3 group, it is called alanine. So these are some of the examples for amino acids. That is called the what is the R group present here, CH2OH. So here the R is in one there is alanine, glycine, R is H. In alanine, R is CH3. In serine, R is CH2OH. The other 3 groups are same. The 3 groups are same. So like that, we have different basic amino acids, 20 basic amino acids. How many amino acids are there? There are 20 amino acids present in proteins. These are called proteinogenic or standard amino acids. Of the 20, some cannot be synthesized by one's body. So all these 20 amino acids are not synthesized in the body. So these are essential amino acids. Must be supplied through the food. Hence are called essential amino. This is a very important question. What are essential amino acids and non-essential amino acids? So essential amino acids which are not synthesized in body or synthesized in the body, which are supplied through diets or supplements, through tablets, they are called non-essential means which can be produced in the body. Some can be synthesized by one's body, hence are called non-essential amino acids. Of course, this is a list of essential and non-essential amino acids. Phenylalanine, valine, threonine, tryptophan, isoleucine, methionine. These are coming under essential amino acids which are not prepared in the body. These are non-essential amino acids which are prepared in the synthesized in the body. Of course, properties of amino acids, whether they are acidic, neutral, or alkaline. So, and the concept of jitter ion we discuss here. Amino acids are jitter ions or hybrid ions. That means jitter ion containing both cation as well as anion. Where they are dissolved in aqueous medium, they undergo ionization and possess both positive and negative ions. So, that is called a jitter ion. That means if H is going from H plus, so here we'll see. Yes, amino acids are amphoteric. Why it is called amphoteric? Contains both the basic as well as acidic groups. So, basic as well as acidic groups. Okay, alkaline medium they donate. So, in alkaline medium, what will happen? They donate one H plus from this, making it a negatively charged. So, donate H plus ion, gain negative charge and behave as a acids. Okay. Whereas in acidic medium, they accept a proton from ammonia and behave as a negative positive charge and behave as a base. So this is the properties of amino acids. Of course, the classification of amino acids based on their charges. Neutral means no charge, acidic and basic. These are some of the examples for different amino acids. Now, classification of amino acids as acidic, basic and neutral. Depending on the relative number of amino acids, carboxyl groups in a group in a molecule. Equal number means neutral. If both NH2 and COH groups are same in number, it is called neutral. If NH2 groups are more, it is called basic. If COH groups are more than NH2 groups, it is called acidic, of course. Non-essential amino acids which are synthesized in the body, essential amino acids which cannot be synthesized in the body can be supplied through diet or through supplements. Next is a very important concept is a peptide bond. So what is a peptide bond? When two amino acids join together, it loses a molecule of water forming NH2COH. That means from a molecule of NH2COH. Now you see it loses a molecule of water. The bond so formed is called peptide bond. Here, this is a COH group of one amino acid, NH2 group of another amino acid. So, it loses a molecule of water, HOH. Resulting minus H2O, we will get a CO in H bond. So, which is enclosed by this yellow color, that CO in H bond. That is called a peptide bond. So, that means when two amino acids join together, resulting in one peptide bond. When the three amino acids join together, we will get two peptide bonds. That is called a dipeptide. So, if you increase like that, it increases like that tripeptide or so on polypeptide. That polypeptide is nothing but the protein. Understand? So, that is the protein is nothing but a peptide bond. Peptide, dipeptide, tripeptide, polypeptide is the protein. So that is proteins. These are derived from Greek word proteos, meaning prime importance. So proteins again, they are macromolecules and polymers of amino acid. So how do you define a protein? Is a polymer of amino acid or polyamino acids. Proteins are nothing but the polyamino acids. So these proteins are macromolecules and the polymers are monomers. There are heteropolymers made up of different arrangements of hundreds and thousands of 20 standard amino acids, just like how 26 alphabets make a very large number of words. These 20 standard amino acids only by different arrangements, they give hundreds of thousands of amino acids, just with 20 standard amino acids. These are linked by peptide bonds. The polymeric chain of amino acids is also called polypeptide chain. That is nothing but a protein. So there are four types of proteins: primary structure, secondary structure, tertiary structure, and the quaternary structure. Now we will briefly discuss the structure of proteins. So that means primary structure represents only the sequence of amino acids. How the amino acids are joined together one by one in a line. Secondary structure means like a helical structure. So you will get NH bonds and OH bonds. This is a helix, alpha helix. Tertiary structure means regular folding. So how two secondary structures are folded together, resulting in a tertiary structure. Where this is a beta. Whereas the quaternary structure, that means the more number of foldings results in the quaternary structure. So this is the structure types of structure. Primary structure include this is only the regular arrangement. That means in a stage alanine, thymine, cysteine. Okay, like this. They are all in one line. So that is called the primary structure, which represents the yes, of course. Last one is called the one important biomolecules is the nucleic acids. So what is this nucleic acids? These are all biopolymers are essential for the forms of life. So the term nucleic acid again is the overall name for DNA and RNA. The two important one is deoxyribonucleic acid and oxyribonucleic. What are nucleic acids? Again they are nucleotides. Polynucleotides. Nucleotides contain again three parts: ribose sugar, the pentose sugar, one amino group, and phosphate. So of the three groups are there, it's called a nucleotide. So this is they are composed of nucleotides. Therefore, nucleic acids is polynucleotides, which are the monomers made of three components. What are the three components? A nucleotide contains three parts: 5-carbon sugar, a phosphate group, and a nitrogen base. So you know very well about this nucleotide. The polynucleotides nothing but nucleic acids. There are two types: DNA, RNA. What is the difference? Structural difference between DNA and RNA. Deoxyribonucleic acid. If oxygen is missing, that is called deoxyribonucleic acid in the ribose. Of course, this is there are DNA contains 4 bases: adenine, guanine, cytosine, and thymine. RNA also contains 4 bases. First 3 are common. So that means in DNA, what is this? Instead of thymine, uracil will come. That is the only difference. Of course, adenine, guanine, cytosine, thymine, and uracil. So this is the structure of nucleic acid. Nucleotide and the nucleoside. This is nucleoside means what it is, a base and a sugar only. So phosphate is missing. So only these two units are there. We say it is nucleoside. Nucleotide means phosphate in also should be present. That is the polymer of this nucleotide only. We call it as a nucleic acid. Okay. Of course, sugar formation of a dinucleotide. So of course, sugar phosphate is there. When two nucleotides are joined together, we will get a dinucleotide. So polynucleotide is nothing but a nucleic acid. So it's a double strand structure, helical structure of DNA. How the two helix are joined together. How they are connected by a triple bond GC, GC. That means guanine, cyanide, cytosine, adenine, thymine, adenine, like that. Of course, these are the two types of structures: RNA, DNA. This is the DNA structure. Last but not the least is the vitamins. So what are vitamins? Again, these are certain compounds which are required in small amounts in our diet, but their deficiency causes specific diseases. Okay, and are called vitamins. So the compounds which are required in small amounts in our diet, the deficiency of which causes certain diseases are called vitamins. Okay, again there are classification of vitamins as A, B, C, D. A, B, C, D, and some are named as subgroups B1, B2, B6, B12, and excess vitamins is also harmful, and vitamin should not be taken without the advice of doctor. So there is a table, vitamin table. That means what is the source for vitamin, what is the deficiency disease caused by the deficiency. For example, vitamin A. What is the disease caused by the deficiency of vitamin A? Vitamin C, blindness. Vitamin A, which is present in carrots. Okay, so like that, the table. Again, water soluble vitamins and fat soluble vitamins. Classification: fat soluble vitamins which are soluble in fat. Examples: vitamin A, D, E, K. This is a very important question. Water soluble vitamins, B group vitamins, and vitamin C are soluble in water. These must be supplied regularly in diet because they are readily excreted in urine and cannot be stored. So in our body. So this is the definition of vitamins and the classification of vitamins as a water soluble and fat soluble. Okay, the table also is there. Just you have to go through. What is the name of the vitamin, source, and deficiency disease? Vitamin A is readily available in fish, liver oil, carrots, butter, and milk. Vitamin B1, vitamin B2, riboflavin, thiamine, vitamin B6, pyridoxine, vitamin B12, meat, fish, egg, and carrot. So pernicious anemia, if it is deficient, or BC is deficient in hemoglobin. Vitamin C, of course, is ascorbic acid, citrus fruits, not amla and green leafy vegetables. Scurvy, that is a disease. Vitamin D, exposure to sunlight, fish and egg yolk. Okay, rickets, bone deformities. What is the deficiency? So vitamin E, K, these are the sources and the diseases. Okay, so thank you very much. Now I will wind up.